Welcome to Maths with EJD. In this video, I'll be talking about inverse iteration method, computation of eigenvalues and eigenvectors. And I've been talking about some of these methods, uh, you know, for eigenvalues and eigenvectors all along. And in the previous video, I talked about method, power method. Another method will be what we are considering now, which is the inverse iteration method. Then there is the QR method, and then the Rayleigh quotient method. Rayleigh quotient method. Okay, so let's see what the inverse iteration method, which is also known as the power shift method, is like. Inverse iteration method. So the inverse iteration method is a numerical technique used to find eigenvalues and eigenvectors of a matrix, especially the smallest eigenvalue in absolute value. That is, we don't care whether it's negative or positive. We're just interested in absolute value. So this method is particularly useful when the matrix has closely spaced eigenvalues, or when finding the largest or smallest eigenvalues in magnitude. So let's look at the steps. Steps involved in this. First, we choose an initial guess for eigenvector V naught, and we have to ensure that it is non-zero. It can be anything, but it should be non-zero. Then two, we select an initial guess for the eigenvalue, call that lambda. Then three, we solve the system, solve the system which is a minus lambda I vk plus 1 equals vk to obtain the next approximation. Next approximation, vk plus 1. That's what we are looking for there. Then 4, normalize the vector vk plus 1 to prevent overflow or underflow and ensure numerical stability. Then 5, estimate the eigenvalue. You can take that as the first iteration, right? And then we keep counting. So lambda 1 is approximately VK transpose VK plus 1 all over VK transpose VK. So that's a very useful formula in the process. Then we go for step 6. So step 6, repeat steps 3 to 5 until convergence of VK plus 1 and lambda. I mean, you can call it, I think we can call it lambda K, right? So for instance, this can be lambda K plus 1. And lambda, okay, so let's call this lambda K plus 1 for the sake of consistency. Okay, so we have that there right now. So let's take an example. So we'll take the usual matrix. Given A equals 4, 1, 2, 3. Okay, so we take V naught to be 1, 1. Okay, and lambda is 2. So that's what we are taking here. Then we now, so we have A minus lambda I into V1 equals V naught, right? Based on what we have up there. So this is, A is 4, 1, 2, 3 minus lambda I, that's lambda 0, 0 lambda. Okay. Okay, yeah, we already have lambda, right? Lambda is 2. So lambda is 2. So this is 2, 2 here. So all this into, so V1 is what we need now. So we can say that is V1x and V1y. And V0 is 1, 1, based on what we have here. So that we can tidy this up to be 4 minus 2, 2, 1 minus 0, 1, 2 minus 0, 2, 3 minus 2, 1 into V1x, V1y equals 1, 1. So if we expand this, we have V1x, V1y, V1x, V1y, because we have 2 rows here. So we write it twice, right? So this is 2, 1, 2, 1, and that's equal to 1, 1. So if you look at the 2, you actually have V1x plus 2V1x plus V1y equals 1. Again, 2V1x plus V1y equals 1. So we can take any one of the two. I mean, they are the same basically. So since they are basically the same, both equations are identical, right? Both equations are identical. So we can arbitrarily choose. So let's imagine V1x to be equal to 1. So that means we have 2 into 1 plus V1y equals 1. So V1y is equal to 1 minus 2. So V1y is equal to minus 1. So in essence, V is equal to So now that's going to be our V1, right? So V1 is equal to 1 minus 1, like this. 1 minus 1. So the next thing is to normalize. So normalize V1. So I mean, here we could choose anything. We could have said V1x is 0 or V1y is 0, anything. So here we have chosen 1. So it gives us 1 minus 1. So to normalize V1 now, that's to ensure numerical stability and prevent overflow or underflow. We normalize V1. So that means absolute the norm of V1 is equal to square root of 1 squared plus minus 1 squared. All of that is square root of 1 plus 1, and that is square root of 2. So with that, now we have the new V1 to be 1 over root 2. 1 over, I mean, the norm thing is about the fact that V1 is now the old V1 over the norm of V1, and that is equal to 1 minus 1 divided by root 2. That's like 1 over root 2 into 1 minus 1. So if we like, we can leave it that way, or we can say 1 over root 2 then minus 1 over root 2, like that. We can also normalize, but we can have it this way. So the next thing we want to do is to estimate the eigenvalue, estimate the eigenvalue. So with that, we have lambda. Let's say the first lambda now, lambda 1, that is V naught transpose V1 all over V1, I mean, all over okay, so we can do, let's make it V1 transpose V transpose, up here, right? Yeah, this is the same thing as VK plus 1 is approximately VK transpose V transpose A VK all over VK transpose VK. So same. So VK plus 1 is the same thing as AVK, basically. That's all I need to establish there. So we're back here now. We have V1 transpose A V1 all over V1 transpose V1, like that. So see, V1 transpose A V1 is simply V1 transpose. We already have V1 to be that, right? So V1 transpose is 1 over root 2 minus 1 over root 2 into A, which is 4, 1, 2, 3. Okay. Then we have V1. V1. So V1 is 1 over root 2, then minus 1 over root 2, like that. I mean, I shouldn't have restricted. I mean, it is what it is. So we have what we have there. So, so we can take care of this first, right? We can take care of this first. So we have this to be 1 over root 2 minus 1 over root 2 into, so because this is 2, right? We can have 1 over root 2 minus 1 over root 2, 1 over root 2, then minus 1 over root 2, and then we impose this over 8. It is 4, 1, and this is 2, 3. Oh no, that should be twice. That should be twice. Okay. So this is not necessary. Yeah, because we have just 2 rows. So we'll just try that twice. So this is 1 over root 2 minus 1 over root 2. Then like this. So this is 1 over root 2 minus 1 over root 2 into, so this is 4. This is 4 plus root 2. 1 times Okay. Yeah, I think I was right. The root is confusing a bit. So let's go back to what we had. Yeah, so this is 4, 1. Then this is 2, 3. Yeah, this is okay. So this is 1 over root 2 minus 1 over root 2 into, this is 4 over root 2, right? Minus 1 over root 2, that is 3 over root 2 up there. Then down here we have 2 over root 2 minus 3 over root 2. That's minus 1 over root 2, like that. Okay. So we can now take care of this. And this is just going to give us a single value, I believe. So this is 3 over root 2 minus 1 over root 2 multiplied by 1 over root 2 here, and minus 1 over root 2. So that's going to give us just one thing, and that's V transpose A V1, right? So this is V transpose V1 transpose A V1. So that's equal to, this is 3 over 2, 3 over 2 plus 1 over 2. You know, when we multiply all that out, 3 times 1 is 3, root 2 times root 2 is 2. Minus and minus is plus, 1 times 1 is 1, root 2 times root 2 is 2. So LCM is 2. We have 3 plus 1. And that means that V1 transpose A V1 is equal to 4 over 2. So, and that is equal to 2. So we have that. You know, what exactly we're looking for is, we need, this is what we need here, right? So we also need V transpose V1. So V1 transpose V1 is actually V1 transpose V1 is let's see, what's V1 now? Okay. Yeah. So that's basically 1 over root 2 minus 1 over root 2 multiplied by 1 over root 2 minus 1 over root 2. And that is the same as 1 over root 2 minus 1 over root 2, and put this over it, 1 over root 2 minus 1 over root 2. So that means that V1 transpose V1 is equal to 1 times 1, 1, root 2 over root 2 is 2. Minus and minus plus 1 times 1, 1, root 2 over root 2 is 2. So LCM is 2, that's 1 plus 1, all over 2. So V1 transpose V1 is equal to 1 over 2. I mean, equals 2 over 2, 2 over 2, which is equal to 1. Now, what does that tell us? It means that the lambda we are in need of, you know, so lambda 1 now is approximately V1 transpose A V1 all over V1 transpose V1. And that is, for the first one, we got 2, right? For the second one, we got 1. Okay. We got this 1 here. So this is 2 over 1. Therefore, for the first iteration, lambda 1 is 2 over 1, which is equal to 2. I mean, from what we know about that matrix, right, the two eigenvectors are 2 and 5. So we can actually repeat this process for as long as we want. But, I mean, we could, so you know the steps already, so you can just repeat that. So the next step now is repeat the process, repeat the process if necessary. Or from the background knowledge, we know this is it. So we can now say that at this point, okay, repeat the process if necessary, right? So we can say that at this point, the eigenvector, that's our V1, right? The eigenvector V1 is 1 over root 2 minus 1 over root 2. That's about the same thing as 1, 1, if you like, okay? So has converged, because we chose a value. In fact, that's exactly that value, has converged, and the eigenvalue lambda 1 equals to is stable. Okay, so we can then conclude. So we conclude that lambda is equal to 2 and the eigenvector corresponding to it is equal to 1 over root 2 minus 1 over root 2. Okay, so that's how that goes for shift inverse iteration method. Okay, inverse iteration method, that is it. So thank you for listening so far. If you have not subscribed, please go ahead and do that. Hit the notification bell so you can always get alerted each time a new video is released. If you have subscribed, thank you so much. Comment, let me know how helpful these videos are for you, and let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then like and share so that more people can have access to these great teachings. Bye.